will look at this further. So you can see this is basically like a vertical truss, and you can have bracings only in one direction. If the bracing is only in one direction, then it has to carry either tension or compression. But if you have bracings in two directions, generally we assume that the compression bracing has buckled and only the tension bracing is effective at a given time. And when you have this arrangement, because it's connected to the middle of the beam will have additional forces acting on it. So in that sense, the size of the beam may have to be increased because there are additional loads acting on the beam. Then if you look at all these, all the bracings that you have seen earlier, the height of the bracing is limited to one floor. But if you look at this one, the height of the bracing is not limited to one floor, and it is also not limited to one bay. You can see it's from one end of the building to the other end of the building. And because of that, the efficiency is high. The reason is the frame can mobilize the columns at extreme ends so that the bending moment that can be resisted will be very high. But the problem is these bracings can be seen. So it should become an architectural feature to if you want to use these large bracings. So you will have to work with the architect, and architect should be willing to make it a structural feature of the building. Then the next important thing is how these bracings behave. Now, when these lateral loads are acting, the chords in the normal truss, the top chord and bottom chords can be in the horizontal direction, whereas in these vertical trusses, the chord members are in the vertical direction. So these are the chord members. This side and this side are the chord members. And when the loads are acting, the type of deformation that you get is like a cantilever. We call it the flexural deformation. It's like a cantilever. Then there will be deformation of the bracing elements. And the deformation of the bracing elements will give a shear deformation shape. So what is the difference between flexural deformation and shear deformation? Gaurikantan, are you there?
Yes, sir.
Do you know the difference between flexural deformation and shear deformation? If you don't know, say, I don't know.
Maybe flexural deformation is...
Louder.
Can you hear me, sir?
Yeah.
Maybe the flexural deformation can be occur in the chords, but the shear deformations...
Actually, it comes with the shape. Right? It comes with the shape. And if you look at the shape, this is a cantilever mode.
Yes, sir.
In cantilever mode, the rotation at the base is 0. Rotation at top is maximum. In the shear mode, rotation at the base is maximum, rotation at the top is 0. So that is the main difference between flexural deformation and shear deformation.
Okay, sir.
So when you combine, now in the actual building, you can't have two different deformations. What is the reason for saying that? In actual building, you can't have two different deformations. What is the reason? So all these members are connected by a flow diaphragm, flow diaphragm, or a rigid flow. So because of that reason, you can't have two different deformations, because the flow generally behave like a rigid diaphragm. The flow generally behave like a rigid diaphragm. Okay. So because the flow behaves like a rigid diaphragm, you can't have two different deformations. Then what happens? At the base, this connection is more robust. So at the bottom part, the deformation will take the cantilever shape. At the top part, now you can see this is having lesser deformation. That will start governing. So you'll find, rather than having the cantilever shape, we are having a shape where we have some deformation in the middle, and as you reach the top, the deformation is decreased. So here you have very little increase. In the middle, you will have a substantial increase every flow, and then you are going to have a lesser deformation as you come to the top. So the shape is not a cantilever shape. In the bottom part, the shape is like this. In the top part, the shape is like this. It's a combination of those two shapes. And understanding this is very important, because in buildings, we can actually see this particular type of behavior. Can you understand it?
Yes. Yes. Yes, sir.
Charmika? Who is Charmika? Who is Dayani Aponso?
Yes, sir. Can I understand?
You can understand it, right? Okay, good. Now, deflected pattern, when subjected to horizontal loading, brace frames tend to behave like vertical cantilevers. The effect of columns or chords, axial deformations, is to cause the flexural configuration of the structure, as shown in the figure. This will have the maximum slope at the top. Due to the deformation of web members, diagonal members or horizontal girders is to cause the shear configuration, and this will have the maximum slope at the base. So the deflected shape that occur as a result of this interaction is a combination of flexural and shear behaviors, depending on the relative member sizes, and can be of the shape shown in the figure, that is the final shape that we have seen. With these favorable behaviors, what is the important thing? It is possible to use bracings even in very tall buildings having even more than 50 floors. So we can have this even in tall buildings having more than 50 floors. Sorry about this full stop. In presentations, generally we should not have full stop at the bullet points. I have missed that. Now, when you look at this particular type of construction, what we call brace frames, steel is the ideal material, because some of the bracings can be in compression, the others can be in tension. Steel is a very good material in carrying tension. It is a good material in carrying compression as well, but because we are using slender sections, not very thick sections, steel has a problem that is the tendency to buckle. So steel is not a extremely good material in carrying compression, although individually it can carry compression. But to optimize, we use thin sections. Because of that, steel is not the best material to carry compression, whereas steel is a very good material to carry tension. So brace frames are generally constructed out of steel, but sometimes you might get situations where even concrete has been used. So the type of structure that we generally get with concrete is rigid frame structures. Rigid frame structures. So in these rigid frame structures, columns and beams are connected with moment resisting connections. Now you know that when we cast reinforced concrete, in situ cast it, we have continuous reinforcement, so automatically the structure can resist bending moments, and at each junction it's possible to share the bending moments acting on the junction. So we call it monolithically cast or the in situ cast, and it has a moment carry capacity at each connection. Whereas in steel, it is not that easy to create a moment resisting connection. So because of that reason, rigid frame structures are particularly suitable for reinforced concrete. The main advantages of a brace frame is that, you know, we are having beams and columns only. We are not having any diagonal members. But the frame can carry a reasonable lateral load. So we can actually have almost complete freedom when you are planning the doors and windows, and also when you are planning partitions and so on, we get a lot of freedom. So the column spacing can be in the range of 6 to 9 meters. Then why do we say 6 to 9 meters? 9 meters is a fairly high span. But in tall buildings, generally, we like to use spans in excess of 6 meters. What is the reason? The reason is we can then isolate the foundations. Otherwise, you know, if you have columns too close, you might find that the foundations are overlapping each other. So the column spacing could be from 6 to 9 meters. And if you are using rigid frame structures to resist loads, generally wind loads up to 20 floors can be resisted by using this particular arrangement due to structural efficiency. But one of the problems is at the top, you can see the wind load is very small. This wind load is acting. So the moment due to wind load is not very high. And as you come down, if you take a place here, all these loads are now creating bending moment. So the bending moment generated at this level will be fairly high, and at this level even higher. So we are talking about 12-15 story building, and all these wind loads are now acting at this particular level. So there will be a big moment acting at this level, and part of that moment could be transferred onto the beam as well. The beam is cast together with column. So this moment acting at this particular level, first floor level, will be transferred to the part of the moment will be transferred to the beam as well. And due to this additional moment transfer, sometimes you find that the beam size has to be increased. And in a building where you are having 15 floors or so, generally we like to make a reasonable investment to make a good formwork initially, knowing that we can reuse this formwork 12 to 15 times. But if you are going to have bigger beams at the ground floor level or close to ground floor, then you will find that this same formwork cannot be used from the first floor itself. So that might be a disadvantage, and because of that reason, we generally do not try to rely on rigid frame structures for fairly tall buildings. It generally about 10 to 12 stories, it may be okay. But in the modern buildings, you will always find that because we need lift for circulation and so on, these rigid frames are supplemented by the walls. So basically, the rigid frame will become a restraint structure. So if you have a rigid frame structure without any shear walls, then you have to design it as an unbraced structure. Unbraced. That means the frame can have lateral deformations, and if excessive lateral deformations occur, there's nobody to resist the movement. There's nobody to resist the movement. So because of that reason, when you have rigid frame structures, you have to design it as unbraced. Whereas if there are shear walls connected to this structure, to the floor diaphragm, then we can design the frame as braced. That means the lateral deformations are controlled by some other element, not by the frame itself. So we can have two different situations. If the rigid frame structure is on its own, we have to design it as unbraced. Whereas if it is connected with shear walls, we'll be able to design it as braced structure. Right. Okay. So basically, we'll move to the next one. So basically, reinforced due to the need for beam column moment resisting junction, rigid frame brace lateral load resisting system is ideally suitable for reinforced concrete buildings. And so you might need larger beams towards the bottom. And how about the column? Generally, columns are anyway will be bigger, closer to the ground level, and it will not be a major problem when it comes to formwork and so on. So because of that reason, the bigger columns at the ground level is not considered as a major problem, whereas larger beams at the ground level is considered as a problem. So even in a 40-50 story building, the general experience is we'll use the same size beams throughout the height, if the floor arrangements are similar in all floors. Right? So the same beam size does not change in a tall building, but column sizes can change because as you come closer to the ground, there will be a drastic increase in the bending moments and some increase in the axial forces as well. So what is the next structural form? Now, when you have a rigid frame structure, so I said we have to design it as unbraced. But if you have a lot of masonry walls, that will fill these voids in the panel so that it can add some extra stiffness to the structure and also prevent excessive deformations. Then we call it infill framed structures. And when you have infill frames, and if you are sure that the infill frame is going to be there until the end of use of this building, then you might be able to design the concrete frame as a braced frame, whereas if you think that there's some danger of this masonry being removed, then we can still design the frame as unbraced. So it can be designed as braced or unbraced, depending on whether the partitions are going to last until the end of the use of building or not. So when you consider the stiffness due to masonry infill panels, the design becomes simpler and also might become economical in certain situations. So when the lateral loads are acting, what happens is there will be some compression forming in the diagonal direction. So this compression can actually ensure that the deformation of the structure is controlled. The deformation of the structure is controlled because you can see here there will be a compression zone here. When you try to deform it, there will be a compression zone here, and that compression is actually resisting the lateral movement of the infill frame. But there's a downside as well, and that is, the quality of masonry is so important, so as the workmanship. So if you have the infills without openings, then you will be able to design the structure as braced and design it only for vertical loads, because the lateral stability is now provided by the infill masonry panels. One of the big problems associated with these infill panels is, when you are constructing the building today, you might have good control over the building, but over a period of time, 20-30 years, the owners can change and a lot of things can change in the building. And in such situations, there's a possibility of some of these masonry walls being removed to make way for the alterations. So in such situations, if you have not designed the frame to be on its own, you might have some failures occurring in the brace frame. So you have to be careful, and you will be using the panels for which you are sure it's going to last there. And so at places like lift core, the walls surrounding the lift core may be out of masonry, because that type of locations, the chances of the masonry wall being removed is lesser to a certain extent. So because of this danger of accidentally or deliberately removing the masonry panels, we do not rely 100% on the infill masonry for lateral stability. And what we do is, we consider this as a supplementary system. So when you are designing the lateral load carrying system, due to the presence of masonry walls, you will have some advantage, but you will not try to make the full advantage of this masonry infills, due to the chance of it being removed as the building is used. Right. Now we look at another type of application, and this is called shear wall. So what is the main function of a shear wall? Is it to carry shear or is it to carry flexure? Dilshan? So I asked the question, what is the dominant force that will be carried by a shear wall? Is it in flexure or is it in shear?
Shear.
Shear. Dilshan, is it shear or flexure?
I think it is shear.
Shear. No. Actually, what happens is
It is shear, sir.
no. Actually, what happens is when you have a wall, it will be resisting a huge bending moment, and shear may not be the governing criterion. The reason is when the wind loads are acting here. Now, how do you calculate the moment due to wind? W multiplied by L, and for each W you have to multiply it by the height. So you will find that the bending moment is a dominant effect on the shear walls. But in addition to that, it will carry the lateral load as a shear force as well. So when the lateral loads are acting, it can cause significant flexure on the shear wall. But in addition to that, it will carry whatever the shear, and you have to add it up. And this is a simple addition, whereas this one, you multiply it by the height and then add it to the moment. So because of that reason, the bending moment is dominant in shear walls. But shear also can be some value. So although we call it shear wall, the dominant force will be a bending moment. So we like to fix shear walls at the base. Then only we can ensure that the shear wall behaves as a true cantilever. So when you look at shear walls, the shear walls can be isolated shear walls like this or a combined shear wall like this. So what can you say about the flexural moment carrying capacity? Let's take the wind is blowing in this direction. Let's say this is x direction. Can you see the mouse movement?
Yes, sir.
Yes, sir.
So if the wind is acting in this direction, what will happen? Can this wall resist the wind load, or can this wall resist the wind? Which wall can resist the wind? Say this is B, this is A or B. The wind load will be resisted by B. Why? It is having a fairly high second moment of area about the axis of bending. So if the wind is acting like this, what is the axis of bending? How do you find the axis of bending? How we find the axis of bending is by using right hand corkscrew rule. So what is right hand corkscrew rule? It is, you have to take your right hand and show the direction of the moment with the thumb and with the fingers. Then the thumb will show the direction of thumb will show the axis of the moment. Thumb will show the axis of the moment. So if the loads are acting in this direction, then this wall will be carrying those loads. The reason is this wall cannot resist those due to very low second moment of area, whereas this can resist these wall loads. So when this resists, what is the direction of the moment? You can show the direction of the moment with fingers, and then the thumb will show the axis of bending. The thumb will show the axis of bending, and axis of bending will be like this, in that direction. So when the wind loads are acting this way, this wall is capable of resisting the bending moment generated, and the axis of bending will be like this. Is that clear to you?
Yes.
Yeah. How about Ranavaka? Can you
Yes, sir.
understand?
Yes,
Can you
sir.
understand that? Right. Okay. Now I can come to the next point. So let's say we are having a wall having a length of say 6 meters, or we say 4 meters. We are having a wall having a length of 4 meters. The thickness of the wall is 250 millimeters. Right. So we are having a wall of 4 meters of length, 250 millimeters of thickness. And if it is resisting the wind load as this particular wall is doing, then this is the axis of bending. For this axis of bending, we can calculate the second moment of area, which is given by I is equal to 1/12 BH cubed. And if you calculate the I value is 1/12. B is 250, that is the breadth of the wall. H is the length of the wall, 4000 cubed. So you can calculate the second moment of area above the axis of bending. And axis of bending is at the center here. And I said this wall is 4 meters of length, 250 millimeters of thickness. And we can have to find the axis of bending. And axis of bending is here. And it is then the second moment of area for this wall having a length of 4 meters, width of thickness of 250 millimeters will be 1/12 BH cubed, and the thickness of the wall is 250 millimeters. Length of the wall is 4000 millimeters. So the answer that you get, if you have calculators, you can see what is the answer for this 215 to 4000 cubed divided by 12. So the answer is 1.33 meters to the power 4. I for this wall is 1.33 meters to the power 4. Right. Now let's take another element. Let's say this is a fairly tall building, and the size of the column is 1 meter by 1 meter at the ground level. And if you have a column of 1 meter by 1 meter, again we can calculate the second moment of area. I column is equal to 1/12,000 multiplied by 1000 squared. The reason is the cross section is 1000 millimeters by 1000 millimeters, and when you calculate the I value, it becomes 1000 to the power 4 divided by 12. So the answer you get is 0.00833 to the meters to the power 4. The answer that you get is 8.33 into 10 to the power 10, or which is equal to 0.00833. Now we have to compare the I value that we obtained for the shear wall, which is 1.33, with the I value that you can obtain for a column of 1 meter by 1 meter. The column of 1 meter by 1 meter gives an I value of 0.00833, whereas the 6 meter long wall gives a second moment of area of 1.33 meters to the power 4. Now you can clearly see the difference between the efficiency of the wall and the column. Column is a fairly large column, 1 meter by 1 meter, whereas the wall is having an area of 250 by 4000. So if you look at 4000 multiplied by 250, the answer is 100,000. The area is 100,000 millimeter squared. And when you compare it with 1 meter by 1 meter column, again the area is the same, but when you calculate the I value of the wall, 1.33 divided by 0.00833, you can see the wall is 1,596 times stronger than the 1 meter by 1 meter column. So 1000 to the power 4 divided by 12. I'm just checking whether this value is correct. Yes, correct. So you can see the cross-sectional area wise, 4 meter wall having a width of 250 is equal to a concrete column of 1 meter by 1 meter. But when it comes to resisting the lateral loads, this wall can be very much more effective than the column. The reason is the wall is having a fairly high second moment of area above the axis of bending. So now you can see why the shear walls can be very effective in resisting bending moments. The reason is the bending stress for an elastic material is given by MOVZ, and Z is equal to second moment of area divided by the distance to the extreme fiber, say Y1 or something. So basically, when you look at the section modulus Z value, you will see that the Z value for the wall is very large. So even if the wall is having a big moment, the stress due to that moment will be lower. So because of that reason, we like to use these shear walls or concrete walls in buildings, and we can very effectively do that by arranging the shear walls in a particular way. And the other important thing is the shear wall should be fixed to the foundation. So when you have shear walls, you can have plane assemblies or non-plane assemblies. Plane assemblies, you know, a shear wall mainly in one direction. Whereas non-plane assemblies, you know, the shear walls are in so many different directions. As you can see in the center of this one, then it is, it could become non-plane assembly, because you can see there are shear walls this way, shear walls this way, and so on. So because this I value is very high, most of the wind loads acting on the building will be attracted by the shear walls. So if you have only shear walls, you can think of going up to about 35-story buildings without any major problem. So concrete, reinforced concrete shear walls can be used in fairly tall buildings like 30 to 35-story buildings. It's possible to rely on shear walls. So you will see that because there are partition walls, some of these partition walls can be converted to concrete walls, and because of that, you will find that in many hotel buildings and apartment buildings, you will get shear walls at many locations, and all those shear walls can be used for carrying lateral loads. So when it comes to the design, when we compare the I value of the column and I value of the wall, we got that, you know, I value of the wall is about 1,500 times the I value of the column, although the cross-sectional area is the same. Then if you look at the deflection of a structure, these are all acting in cantilever mode, acting like a cantilever. Then the lateral deflection due to the load delta is given by K times W times L to the power 4 divided by EI. And so because I appears in the denominator and I is a fairly high value for the wall, then you will find now the deflection is actually controlled by the structural member having a higher value for I. The reason is the deflection delta is given by kW L to the power 4 divided by EI. So because I appears in the denominator, even for a fairly high wind load that we proportioned earlier, still the deflection is governed by the wall with high I value. So you'll find that it is possible for up to about 15 stories to make a simple assumption. The assumption is that all the lateral loads will be taken by the shear walls. This particular assumption is not valid when you are going above 15 stories. So up to about 15 stories, so preferably 10 to 15 range, we can say that all the lateral loads will be resisted by the shear walls. So if all the lateral loads are resisted by shear walls, then what can you say about the vertical frame structure? What can you say about the vertical frame structure? If all the lateral loads are carried by the shear wall, then the frame need not carry any lateral loads. So the frame can be designed only to carry the vertical loads, and all the lateral loads can be considered to be resisted by the shear walls. So this is one of the assumptions that you are able to make, but don't make this assumption for any building above 15 stories, because as the building height goes up, you will find that the wall alone cannot resist all the lateral loads, because although wall acts like a fairly rigid structure, at the base level it's a pure cantilever. So as you go up and up, you will find that the dominance of the wall is reduced, and because of that reason, we generally don't say in a 30-story building all the lateral loads will be carried by shear walls. We don't make that kind of assumption. Now, if you look at shear walls are carrying lateral loads. Because of that reason, there will be a heavy bending moment acting at the base. And if we have a shear wall connected to the foundation, say pile foundation, and if you have only the bending moment, then one side of the shear wall will be in tension, the other side of the shear wall will be in compression. So what will happen to these piles? The piles will not be loaded vertically downwards, but the piles will be loaded vertically upwards. So that is not desirable, because we generally use piles to carry the vertical loads downwards. So what this means is that we need to have adequate vertical load on the shear wall. Otherwise, the shear wall can go into tension. So it's very important that we have the shear wall supporting some of the slabs, so that the slabs will transfer a lot of vertical load onto the shear wall. So the shear wall will be an axially loaded member carrying a bending moment. So if the shear wall is an axially loaded member carrying a bending moment, then it will be efficient. So it's necessary to make sure that adequate amount of dead weight is transferred onto the shear wall. So when you have both vertical load and the bending moment, then it becomes more efficient, and you will be able to design the shear wall with minimum reinforcement. And another advantage of shear wall is it can actually help in resisting the earthquake induced loads. Again, due to earthquakes, due to very high I value, and also due to our ability to provide additional reinforcement at the ends of the shear walls can demonstrate a very ductile behavior. So because of that, the shear walls can absorb a lot of energy during earthquake, but still survive without suffering damage. There are two reasons for that. One is the ductility. The other one is shear walls will not be subjected to very high deformations because it's a very strong element. And in an earthquake, part of the damage could be due to too much deformation. And when you have shear walls, the deformation of the structure can be controlled to a great extent by the shear walls. So to have enhanced ductility, we'll need some extra reinforcement at the ends of the shear wall. So now we look at the different types of shear wall systems. And if you look at this particular diagram and also look at this particular ratio, here you can see I1A, I2A, I second mode of area 1B, 2B, 1C, 2C. The ratios are all equal. So in a proportionate system, the ratios of the flexural rigidities of the wall remains constant over the full height. So what actually happens here is we are changing the thickness, not the length. We are changing the thickness, but the thickness is changed by the same amount, so these ratios remain the same. Then we call it a proportionate system of shear walls. And in a proportionate system of shear walls, the flexural rigidities of the wall remain constant throughout the height, since the change in thickness are the same at all levels. And when you have this system, we can say that the stronger wall carry more lateral load, the weaker wall will carry less lateral load, and the moment carried by each wall can be easily determined by using a simple equation. So if we say the second amount of area of this wall is I1, the next wall is I2, and the total bending moment acting at this level, base level, is M. Then we can say the moment carried by wall number 1 is given by I1 divided by I1 plus I2 multiplied by the total moment. So the moment carried by this wall M1 is equal to I1 divided by I1 plus I2 multiplied by the total moment. The moment carried by this wall will be M2, and M2 is equal to I2 divided by I1 plus I2 multiplied by the total moment. So we say the moment resisted by each wall is proportionate to the stiffness of the wall. And because of this, you will find that the shear walls are acting like a pure cantilever. And what can we say about a cantilever? Cantilever is a statically determinate structure. Statically determinate structure. So if you have a system of proportionate shear walls in a 10-story building, then you have to design the frame assuming that all the lateral loads will be resisted by the shear walls, which means the frame will be designed only for vertical loads. The walls can have to be designed to carry all the lateral loads, but because the walls are acting purely as cantilevers, you'll find that it is statically determinate. So basically you can design a 10-story building having a proportionate system of shear walls even by doing hand calculations. The reason is the shear wall system is statically determinate, and you can analyze the frames for vertical loads by using simplified subframes. So you will be able to do hand calculations and design a 10-story building having a proportionate system of shear walls. So you can see one of the possibilities of is what we call proportionate system of shear walls. And if you have a proportionate system of shear walls arranged in a symmetrical manner, like in this diagram, so you can see all these walls are symmetrical. Then when you apply the load, lateral loads onto the structure will be non-twisting. So if the structure is proportionate non-twisting, then it's very easy to find the moment acting on each shear wall. The moment acting on each shear wall is a function of the total moment. And what you have to say is if the second moment of area of this wall is I1 about this axis of bending is like this, right? So axis of bending is like this. So if you know the second moment of area of this wall is I1, the second moment of area of all the walls about the same axis is sigma I, then the bending moment carried by this particular wall will be M1 times, M1 is equal to M times I1 divided by sigma I, I1 divided by sigma I. So basically it's very easy to find the bending moment acting on each wall. So if you know the axial load on the wall and bending moment on the wall, you will be able to design the wall. So basically a structure having proportionate non-twisting means the shear walls are arranged symmetrically, then you can actually say the whole structure is statically determinate. So this means that in the case of a symmetrically arranged shear walls as shown in figure, resulting in a non-twisting structure, it is possible to analyze the structure by considering the equilibrium of external moments and shears distributed between the walls in the ratios of the flexural rigidities. So we call it proportionate non-twisting arrangement.
Excuse me, sir.
Yes.
This building is not symmetric in both directions, right? So will that be an issue?
No, actually, you can make it symmetrical this direction by, now here you have a wall. Here you have a wall. Yeah. Yes, you are correct. It is not proportionate. It is not untwisting for loads acting this way, but for the loads acting this way, it's non-twisting. You are correct, right? And the problem comes with these two walls. Is that right? These two walls and these walls. The problem comes with those walls. And if you don't have those walls, then it will be a symmetrical arrangement.
Yes.
Right?
Okay.
That's a good question. So when subjected to horizontal loads, the structure will not twist. It will only move laterally. It will move laterally, but no twisting. So we call it proportionate non-twisting structure, and the structure is statically determinate. Is that clear?
Yes, sir.
Yeah. Anybody else having a question? The important thing is to find the axis of bending. So you have to always show the moment direction with the fingers, and the thumb will show the axis of bending. So for these loads, when you show the moment with the fingers, the axis of bending will be shown by the thumb. So always see that axis of bending is here for individual walls. So at any level I, the total external load acting on the structure Qi will be distributed in the ratio of flexural rigidities, and for this reason the moment also will be distributed in the ratio of flexural rigidities. So generally with when you are doing calculations, sometimes we ignore the value of elastic modulus, because elastic modulus generally tend to be the same for all elements if it is the same type of concrete that we have used. So you will find that generally you can, if you want, you can consider the elastic modulus. If the elastic modulus is the same, you can simply ignore E, but write the equation in terms of I. But when you are writing a general equation, we say EI, because we are talking about the stiffness of the wall. So this is the level is I, say 10th floor, 11th floor is I, and J is the location of the wall. So what happens if we do not arrange the shear walls in a symmetrical manner? Then you will find a new term called center of twist or centroid of wall rigidities. So what happens is the structure, due to the lateral load, will first translate, because we are not applying the load here, resisting the load here. So there is a distance between these two, and that can generate a torsional moment. And the axis is vertical for the torsional moment. So what happens to the structure is structure will rotate. So if the shear walls are proportionate, the displacement at any floor level will be a combination of translation and rotation. And what actually happens is, because the flow is considered as rigid, it will simply rotate. About the center of twist. It is simply rotate about the center of twist. Is that clear? Then the question is this statically determinate or indeterminate? Now we have a structure which translates and twists both. But the shear walls are proportionate, so we are changing the thickness. If you are changing the thickness, its thickness is changed by the same amount for all the walls, or otherwise we are not changing the thickness at all. So the structure is twisting, and the question is it statically determinate or indeterminate? Still the structure will be statically determinate, and we have to find what we call center of twist. And how do we find the center of twist? When we apply the wind load this way, the lateral load this way, what is the axis of bending? Axis of bending is like this. Axis of bending is like this. Here, axis of bending is like this. So what we do is, about an arbitrary center, arbitrary location, arbitrary axis, we take the moment of EI. So we find the value of EI for this wall, multiply it by X, and we do that for all the walls, and divide it by sigma EI. Then we can find what we call center of twist. So this is like finding the centroid. To find the centroid, we say sigma mx over sigma m. Similarly, to find the center of twist, we use sigma EI x over sigma EI. So this way we can find the center about which the building is able to resist the lateral loads, whereas the actual axis of the lateral load may be something else. Then what happens? Then, because these two are not coinciding, the structure will twist. And when the structure twists, the walls on this side will have bigger deformation than the walls on this side. So the walls on this side will have a higher load than the walls on this side. So first the wall translates and then it rotates. This side rotates more than this side. So the walls on this side will have a higher moment than the walls on this side. Is that clear?
Yes, sir.
Yeah. Gaurikantan?
Yes, sir.
Yeah, it's clear, right?
Yeah.
How about Herath?
Yes, sir, it's clear.
It's clear, right? Okay. So basically, the structure is still statically determinate, but we have to find the center of twist first, and then we can find the load acting on each wall, and the load acting on each wall will be due to the translation component. That is the first component. Q carried by each wall is proportionate to the second moment of area, plus we get an additional component due to torsional effect on the right hand side and then on the left hand side. So that this additional effect will be positive on the right hand side. On this side it will be negative. So that's why you get Q times E is this. Q is the total load times E is the torsional moment multiplied by EIC divided by EIC squared. And this EIC term will decide this way it's positive, this way it will be negative. So you will get on one side a smaller force, on the other side a greater force. But because the system is proportionate, still the structure is statically determinate. The structure is statically determinate. Is that clear? So with this equation, now you can find the load acting on any shear wall. So when you know the load acting on any shear wall, you can take the moment about the base and you can find the moment acting at the base level. You can find the moment acting at the base level. Is that clear? Although this looks like a big equation, it's not complicated. So this part is actually from the early equation for translation. And this part is for twisting, because you can see Q1 times E is the twisting moment. And this part will deal with the twisting, the load due to twisting. The load due to twisting can be either plus or minus. So you have to be a little careful there when you are substituting the value for C. For right hand side, you have to say it's positive. Left hand side, you have to say it's negative. Now, if you look at that first diagram, where we had walls in both directions, when this twisting occurs, if you have walls in both directions, here you can see the load is acting here, and this is the center of twist here. So what happens is, now the load is, the twisting moment is resisted by these walls, and twisting moment is also resisted by these walls. So because of that reason, the effect of twisting moment on these walls will become smaller. So you will find that instead of, in the early equation we had only this part. Now if you are considering the walls in the perpendicular direction, then you have to consider the contribution from those walls in resisting the twisting moment. So you will find that you have to modify the denominator of this right hand side dealing with the twisting moment. So this is a twisting moment, And here you have to deal with that by dividing not only by EIC squared, but by EIC squared plus sigma EID squared. And the reason is, if you don't have these walls, then all the torsion has to be resisted by these. But when you have these walls, they also can make a contribution to resisting the twisting moment, and that will give us this particular equation. And in addition to, now this is the load in these walls. How about the load on these walls? The load on these walls are given by only due to the twisting moment. It's only due to the twisting moment, not due to translation. So you will find the load on these walls will be given by twisting moment component, and you have to consider the proportion of the walls in the perpendicular direction. So this way you can work out the loads acting on any wall. And these are the equations that we engineers used before we started using the software structural analysis packages. The structural engineers used these equations to find the loads acting on individual shear walls to design the shear walls. So all these equations will give you an insight into the way that the structures behave when they are proportionate and twisting, proportionate and non-twisting, and proportionate and twisting. In both cases, the structures are determinate, statically determinate, and the engineers use this technique to design buildings up to 10 to 15 stories by considering that all the lateral loads will be taken by the shear walls and the frames will take only the vertical loads. But these days, because the software is available, structural analysis packages are available, we do not do all these calculations manually, but an understanding on the way that the structures behave is important, and you can actually try and understand the actual behavior of the structures by looking at these equations. So what actually happens is, if the structure is proportionate, if you have walls only in one direction, and that is the direction the loads are also acting, depending on whether it's twisting or non-twisting, you can work out the loads on each and every shear wall. And once you know the loads on each and every shear wall, you can do the structural design by finding the bending moment and the axial load acting on the shear wall. So let's say we are having a shear wall and we have done this basic calculation, and we are having a shear wall having a length of say 4 meters. The thickness is 250 millimeters. The length is 4 meters, so 4000 millimeters. And let's say the axial load on this wall is something like 9,000 kilonewtons. The axial load is 9,000 kilonewtons. And the bending moment acting on the shear wall is about 5,000 kilonewton meters. It's about 5,000 kilonewton meters. So let's say we have done the calculations. We have a shear wall having an ultimate bending moment of something like ultimate axial load of something like 9,000 kilonewtons. Ultimate bending moment of something like 5,000 kilonewton meters. How can you find the reinforcement in the shear wall? How can you find the shear reinforcement in the shear wall? What is the method? So there are two ways of actually looking at it. So the easiest way is to consider it as a column. It as a column. And if it is a column, if you know the bending moment as 5,000 kilonewton meters, and then the axial load as 9,000 kilonewtons, what you do is you find MOBH squared and NOBH. MOBH squared is M is 5,000 into 10 to the power 3, 6 divided by breadth is 225 and the length is 4,000 squared. So when you look at that, you also can do this calculation MOBD squared. The answer is 1.388, and then you can find NOBH, that is 9,000 10 to the power 3 divided by 225 multiplied by 4,000. So 9,000 divided by 225 divided by 4,000. So NOBH is 10. So when you know NOBH and MOBH squared, you can find the reinforcement by finding the appropriate chart on the column design chart. I'll use a British chart for Eurocode. Also, you have already used the charts. So using the chart, we can find the appropriate column design chart, assuming something like grade 30 concrete with cube strength of 30. So what you can do is, you can assume that the column reinforcement will be concentrated on the wall, say over something like 0.8 meters. Because this is only 4 meters of length, I will use something like 0.8 meter at the ends as effective. So if it is 0.8 meter effective, then 4,000 minus 800 divided by 2 is 400. So DOH ratio will be 0.9. DOH ratio will be something like 0.9. So what I can do is, I can find the appropriate chart and then I'll stop share this one and then share the chart. So you get a chart like this, MOBH squared and NOBH. And when you are using Eurocode charts, you might get MOBH squared FCU, FCK and NOBH FCK. So let's assume that is a cube strength of 30. And Then DOH is 0.9. MOBH squared is 1.388, somewhere here. And NOBH is 10. And you can see the reinforcement requirement is 0.4%. The reinforcement requirement is 0.4%. So 0.4% multiplied by 0.004 multiplied by 225 multiplied by 4,000 divided by 100, sorry, 0.4% will give a reinforcement amount of 0.004 multiplied by 225 multiplied by 4,000 will give a reinforcement area of 3,600 millimeters squared. And what you do is half of that you will provide in one end, and the remaining half you will provide it in the other end. So each end you have to provide of something like 1,800 square millimeters. 1,800, and if you use 16 millimeter bars having an area of 201, you need about 9 bars. So we can say we are going to provide 10 bars. So on one side you will provide 16 millimeter bars. On the other side you will provide another 5. So altogether 10 at one side, 10 at the other side. So 10 of 16 millimeter bars means 2,000 square millimeters. So the requirement is 3,600 square millimeters. You will provide a concentration of reinforcement equivalent to something like 4,000 square millimeters. Then what will happen to the remaining part of the wall? Now you have the wall of 4 meters of length. At every end over 0.8 meters, you have provided some concentration of reinforcement with 16 millimeter bars. What are you going to do with the remaining part of the wall, the middle part of the wall? In the middle part of the wall, you can provide the nominal reinforcement or the minimum reinforcement, which is 4%. So you can provide 0.4%. That is the nominal reinforcement, 0.4%. With 0.2% on each face. So you will find that 0.4% reinforcement over 1,000 over 1 meter, 1,000 multiplied by 225 multiplied by 0.004 will give 900 millimeters squared every 1 meter length. And when you divide it by 2, because we are providing the reinforcement over each face, you get 450 millimeters squared. And when you divide it by 113, that is the area for 12 millimeter bar, you will find that you have to provide about 4 bars on each face. So 4 bars over 1,000 millimeters means you have to provide 12 millimeter bars over 12 millimeter bars at a spacing of 250 center to center. So if I explain it again, so basically we are having a ratio 1.33. NOBH is 1.388, 1.4, somewhere here. And NOBH of 10, so we are here. So the reinforcement requirement in the concentrated zones will be 0.4%. 0.4% of the total wall area. That is 0.4. 0.4% means 0.004 multiplied by the total wall area, 225 multiplied by 4,000. That gives an answer of 3,600. So if you divide it by 2, because we are going to provide half the area at each end, then you will end up with something like 1,800 millimeters squared. And if you are providing 16 millimeter bars, then the area of a 16 millimeter bar is 200 millimeters squared. So 1,800 divided by 200 will give you 9 9 bars. We can't provide 9 bars on two faces, so we have to provide 10 bars with 5 bars on each side. So 10 bars at one side, you get 2010 square millimeters. On the other side, another 2010. So altogether 4020 square millimeters of reinforcement can be provided when we need only 3600 square millimeters. Then the question comes, what are we going to do with the remaining area of the wall? So generally in walls, we do not use a bar diameter less than 12 millimeters in the vertical direction. Because when you use a bar diameter less than 12 millimeters, generally there's a tendency for the bars to buckle. So because of that reason, generally we use 12 millimeter bars in the vertical direction. So you get 12 millimeter bars, but the reinforcement ratio is 0.4% with 0.2% on each face. So when you consider 0.4% of 4000 multiplied by 225, 1000 multiplied by 225 multiplied by 0.004, you will end up with 900 millimeters squared. That means on each face you have to provide 450 millimeters squared. And when you divide it by the area of a 12 millimeter bar, which is 113, you will end up with having 4 reinforcement over 1 meter, which means a spacing of 250 millimeters in the for the vertical bars. So you can easily, when you know the bending moment and the axial load on the column, this way you can easily work out the reinforcement. Is that clear? Shall I stop sharing this chart? Is that clear? Okay, so I will share the earlier screen. Right. So you can see this is the way that the buildings have been designed before we started using the computers. And when you know the axial load and the bending moment, you can find the reinforcement in the wall as well. Then there's another way of finding the reinforcement requirement on the wall. What is that method? In that method, what we do is we want to see whether the wall is cracked or uncracked. We know if the compression is more than the tension, then the whole wall can be in compression. Whole wall can be in compression. So what you do is, we know the bending formula, MOVZ is sigma is equal to MOVZ, and we can find the Z value for this particular wall. The Z value for this particular wall is 1/6 BD cubed, BD squared 225 multiplied by 4000 squared, and you will find the answer is 0.6 meter cubed. And when you know the second section modulus, so Z value, the bending stress sigma, the maximum bending stress is given by MOVZ, and the value of M is 5000 kilonewton meters divided by Z 0.6. You will get the answer as 8333 kilonewtons per meter squared. Similarly, you can find the axial stress, sigma axial. You can find that by dividing 9000 kilonewtons by 0.225 multiplied by 4 meters. So you will get 9000 divided by 0.225 divided by 4. You get a value of 10,000. So you have an axial stress, compressive stress of 10,000, bending moment maximum stress of 8333, So what you find is then there will be a, on the compression side, the stressors add up, and on the tension side, you have to get the difference, but you will find the compression is more than tension. So the maximum tension will be 18,333. Maximum compression will be something like, minimum compression will be something like 1,667. So the whole wall is in compression. Then the other method of designing is you will consider 1 meter length at the most stressed side, that is 18,333, and then you will find the reinforcement to resist that load of 18,333. So that is the other way of finding the reinforcement requirement in the wall. So every meter length, you will find the load is reducing. So you can find that, once you are coming towards the center, at one moment, you will find that the minimum reinforcement in the wall governs, whereas at the corners, the maximum stress acting on the wall governs. Now, can you understand that method? That is, we consider that the wall is behaving like a element subjected to a vertical load and a bending moment. So what we do is we find the bending moment effect, that is a triangular distribution, and then we also find the axial effect, that is a uniform distribution. So once you add those two up, you can find the actual stress distribution. And if the actual stress distribution is compression everywhere, then you can design the reinforcement by considering meter width along the wall. But if when you add the bending moment and the axial force, if the bending moment is very high and you get tension in the wall, then you cannot use this method directly. The reason is, the moment the wall is cracked, when you get tension in the wall is cracked, and then you have to consider the effect of reinforcement, because in the cracked region, all the forces, all the loads will be carried by the reinforcement. So you will have to be a little careful. So that's why when you are designing shear walls, we try to transfer as much dead load as possible onto the shear wall, so that we can suppress the bending moment acting on the shear wall. Is the second method clear to you? In the second method, we consider that the shear wall is something that is subjected to axial load and a bending moment. And then we find the bending stress and the axial stress. And if all these stresses are compression, then we can design the reinforcement by considering the maximum stress acting on the shear wall. Is this method clear? It's clear, right? Okay. So there are two methods of designing a shear wall. One is considering it as a column. The other one is, considering the stress distribution. Now let's look at non-proportionate, non-twisting structure. Non-twisting means the arrangement is symmetrical, so no twisting. But when you look at the wall, you can clearly see there's something unusual here, because here the length of the wall is not changing, whereas the length of the wall is changed here. Here the length of the wall is same as above, whereas the length of the wall is different here. Then you get non-proportionate. And what happens in a non-proportionate shear wall is, there will be some interaction at these places. Here it's almost okay, because there's the same ratio. But here it's a different ratio. Then there will be certain amount of shear transfer from one wall to the other, and that will make it statically indeterminate. So if you are having shear walls like this, where some of the shear walls are changed in the length, other shear walls are not changed in the length, then the structure becomes statically indeterminate. That means, designing this with hand calculations is not very straightforward. There are methods, but not very straightforward. So we can easily use the computers and work out the loads on the shear wall when this happens. So we'll have a look at that. So when the structure is non-twisting, possible to represent the three-dimensional range was as arranged in a plane and linked with pin-connected links to perform the structural analysis. So basically here, if you look at this arrangement in the building, now this wall number 1 identical, wall number 2 identical, wall number 3 identical, but wall number 2 does not change the length, whereas wall number 3 changes the length. So that means this becomes non-proportionate structure shear wall arrangement, and this is again because the structure is not twisting. Actually, you can convert this 3D structure to a 2D structure and do the analysis. So what we do is we consider half the structure. Because this is a symmetrical structure, we consider half the structure and apply half the load. Otherwise, you can consider the full structure, but then you have to make sure this wall number 1 is lumped together. So either you can lump them, consider the full load. When you say lumping, what we say is, you have to multiply the second moment of area of this wall number 1 by 2, and then assign that value for this particular wall. If you are giving the size of the member and then asking the program to calculate the properties, then you have to specify twice the thickness of the wall, because we are considered lumping two walls together. So this is wall number 1. Wall number 2, again we represent. Wall number 3, again we represent. There's no specific guideline for the distance between these two. Then what we do is, because each of the floor levels, we are having a concrete floor or a rigid diaphragm, the deflection of each of these floors will be the same, and it is non-twisting. That means translation only. So the deflection is the same. Because the deflection is the same, you will find that all these can be linked with axially rigid links, but pin-ended. So we are saying the deflection of this particular wall number 1 is equal to the deflection of the wall number 2, deflection of the wall number 3. And then we apply the load on the structure onto this, because all the lateral loads are resisted only by the shear walls. Frames are not resisting it. So when you do that, you will find that it is possible to for the program to find the bending moment acting on each wall, and then we can design the wall considering the results from the program. So that's the way that you can actually easily convert a 3D structure to 2D. And before these 3D programs were available, people used these methods a lot. Whenever they had this kind of arrangement of shear walls, they converted to 2D and did the analysis and got very accurate or reasonably accurate results, almost the same results that you get in a 3D model. So they got almost the same results that you get in a 3D model by doing 2D analysis. Because before all these 3D programs came, 2D programs, two-dimensional programs were available. So people use these 2D programs and converted these 3D structures to 2D. So what you can gather from this is, when you are doing structural analysis, we are not representing the exact structure, but we are creating a mathematical model of the actual structure. So what you can gather from this example is, we are creating a mathematical model, and the mathematical model can be very different to the actual structure. Here you can see the actual structure is 3D, mathematical model is 2D, but this mathematical model is able to tell us about the bending moments acting on the shear walls with a non-proportionate system where there can be certain amount of interaction between the walls at these levels. And here the interaction will not be that high, but there will be certain amount of interaction because we are changing the stiffness of the walls at these levels, but all the walls are not changed, only some walls are changing. So because of that, there will be certain amount of interaction at these levels. Is this clear? So if you want, you can actually do a simple example by selecting a building like this, and you can actually model it this way, three-dimensionally. You can model it this way, two-dimensionally, and then compare the results and see whether you get the same results. The chances are you will get almost the same result, because the behavior of the structure is non-twisting. Behavior of the structure is non-twisting, but it's non-proportionate. Is that clear? That you can actually convert 3D structures to 2D and do the analysis? Any question on that? You can ask, what is the distance between what is the length of these rigid arms? Pin-ended rigid arms, what is the length? There's no specific length. You can use a reasonable distance so that you can see the results easily on the model. The idea is this rigid arm is not really existing. It is a trick that we use to say that the rigid diaphragm will make sure the deflection of all the walls are the same. It is a kind of a trick we use to tell the program that the deflection of wall number 1, 2, and 3 are the same at a given level. Is that clear? Then, so you can see there are 4 types of shear walls. So that is proportionate non-twisting, proportionate twisting, non-proportionate non-twisting, and then the last one is non-proportionate and twisting. Is non-proportionate, we need the computer, and it's twisting also. Then we definitely need the 3D model. So we actually need a 3D model when the structure is non-proportionate and twisting. So that's why, these days we go for 3D modeling for tall buildings, because even if there's we cannot make it perfectly symmetrical and so on, but we can make it approximately reasonable at the beginning of the design. And then when we do the analysis, we'll need a 3D program.